14, and then I'll move to properties of the regular Radon transform, and then we'll see how far I can go. So Compton scattering is an interesting phenomenon. So this is about gamma rays when you have particles. There are different applications, but the biggest, hottest topic with this application right now is in Homeland Security. In the United States, the government is worried of terrorists bringing in some nuclear materials or whatever and then blow up somewhere. So it's considering how much of cargo comes in every day at seaports and by airplanes and so on, it's impossible to go through every single box. So they're trying to have these detectors where they put a big container and the detector tries to figure out if there is any source of radiation there. And one of the ways to do it is through this Compton scattering. So here's the idea. The goal is to find the source of radiation. Well, you don't know if there is a source of radiation or not, and if there is, then you want to know the size and the location, because there are natural sources of radiation. For some strange reason, bananas are a source of radiation. I don't really know why, but they have some sort of small potassium, maybe that's the reason. So you want to know if there is a high concentration of radiation coming from somewhere, and if there is, then you would open the container and start looking for things. So this is what happens. These are two detectors. These are nowadays digital detectors, digital screens. And they basically register an incoming gamma ray, and they register the energy. And they put two parallel detectors. And the physics says the Compton scattering law says that the angle of scattering, so when the particle hits this detector and this detector, you have the axis connecting the two locations. You know the locations. And in fact, the detectors measure the energy here and the energy here. So there is this law that is a physical law that says that the angle of scattering, the angle between these axes of the flight trajectory originally, can be measured by the difference of the energy here and here, and E is the regular, the initial energy, and C is the speed of light, and N is the mass of the particle at rest and all that stuff. So you can basically measure the cosine of the angle. You don't really know the location. And again, just as yesterday, if you have several sources with the same angle, their input would add up. So what you will be really measuring is the integral along cones, because the only thing that you know is the angle. So in 3D case, you get the so-called conical Radon transform, and you're trying to recover the function from its conical Radon transform. In case of the 2D, if you measure somehow just signals coming from planes, or if you mathematically somehow reduce it to the 2D case, then it would be the V-line transform that we talked about yesterday. The difference between this and what we discussed yesterday with the radiative transport equation is that here, if you think of the math setup, it's different because you're trying to recover the function supported somewhere here from V lines, maybe at different angles, but all breaking at the boundary. Whereas in the problem yesterday, you were trying to recover function supported here where the rays break inside, so the corner of the ray was inside. And mathematically, it's a different problem, but I wanted to show that there are some other examples where this broken ray things play an important role. And it's extremely important that you will see that the properties of generalized Radon transforms are very, very different when you go from integrating along smooth trajectories to integrating something that is not smooth. So integrating along lines, circles, ellipses, yeah, for the purposes of getting exact formulas and so on, the situation is different, but it's substantially different when you're integrating along trajectories that are not smooth. So these broken rays, the V-line transform, so on, they are very different in nature because of the singularity along the path of integration.
Is that more informative, actually?
In some sense, it is. In fact, I will be showing later some numerical reconstructions. Actually, in the paper that I talked about yesterday, let me go back. You see, for example, in this setup, this is the slab. The function is supported here, and I was saying that you have a two-parameter family of broken rays. This is the two-parameter family. They all enter like this and break like this. So if you think about it, you only this one's and this one's. It's basically two angles. From the point of view of the regular Radon transform, if somebody tells you recover a function from two angles of lines, you have all the parallel shifts at two angles, it's nonsense. You cannot do that because it's basically you have a set of measure 0 in angular resolution. You cannot do anything. Now, they have an exact inversion formula in this paper, and they have a numerical algorithm. If you see it there, you look at their numerical reconstructions, it's unbelievable. You know, you say, well, it almost looks like,
it's because of the sharp break.
It's exactly because of the sharp break. So sometimes it hurts you, but sometimes it helps you. So the singularity can help you, but then the math becomes much more sophisticated and harder. Okay, so this is I just decided to put something for the students present in the audience to tell you what kind of math is involved in this tomography problems, and this is by no means a complete list. And I know that many of you come from different backgrounds mathematically. Harmonic analysis plays a role. You'll see a lot of Fourier transforms, Fourier series here. PDEs clearly play a role. Differential geometry, numerical analysis, microlocal analysis, differential operators, Fourier integral operators, integral equations, integral. I mean, some people in this field say that you name your favorite field of mathematics, and I'll give you a problem in tomography related to your field. So it's very vast. Whatever you like to do, you can always find something interesting to work with. So I want to talk a little bit about some very simple properties of the Radon transform, but they have a far-reaching implications. At first sight, it looks very, very simple, but it's very, very important, the implications that you have. So the very first thing I want to talk about is the evenness of the Radon transform. So again, let me remind you the notations. So we're talking about a function. Let's say the function is supported in the unit disk, for example, just for simplicity. And then we're integrating it along lines, and the lines are parameterized by the this is Uniqueness. So by the normal to the line, the omega is normal to the line, and d is the distance, right? So RF omega d is the integral of the function defined in this unit disk along this line, and the same thing is written here. So here's what we're saying in this particular property, that if you change the sign of omega d, if you just look at the minus omega, then if you think of the distance being signed distance, negative distance being it's in the reverse direction, then you have the same line, and algebraically it's even easier to see. If you algebraically substitute d by minus d and omega by minus omega, you get the same thing. And so you will very often see that I will say that the RF omega d is defined on 0 to pi, for example, cross r, not r plus, and sometimes it will be, or another possibility is minus pi pi. Of course, because it's periodic, you can continue it as much as you want by periodicity. So here's the thing, guys. Remember, we had this picture of the sinogram. So if I'm trying to make a graph of the Radon transform, let's say this is minus pi and this is pi. Let's say this is 0, this is 1 for the distance, because beyond that distance you don't touch support, so there is no point of integrating. The function is 0 outside. So if you have the sinogram defined here, you can easily define the sinogram here, right? How would I do it? If, say, you are considering this point, that means that you have this negative distance, you can go to the positive distance and take the other side of the plane for the angle, just by this evenness. So basically, the color of this pixel will correspond to the color of this pixel, the color of this pixel will correspond to the color of this pixel, and so on. So, although the Radon transform seems to be defined in a rectangle like this, you can, once you have it in a rectangle like this, you can define it in the whole plane. Vertically, you would do it by periodicity. So in a way, if you take this, you can glue the sides and define it on a cylinder. But also, you can kind of glue in this direction. And I have in the red asterisks a small quiz. What do you think would I get? If I take this and I glue this to make it nice, I would get a cylinder. Now, what happens if you try to to glue it like this. But remember that this guy goes here, this guy goes here, this guy goes here, and so on. Möbius strip. You'll have to twist it and then glue it, right? So the Radon transform is defined on the Möbius strip. So if you thought that Möbius strip is something very, very abstract and useless stuff that mathematicians play, turns out that when you go to a doctor and they do measurements, the measurements live on the Möbius strip. I'm not going to use this for any particular reason, but I always think that this is a very nice example that anything that you think is too abstract in mathematics eventually shows up somewhere in applications. Okay, so there are a couple of invariances related to the Radon transform. The first one is the shift invariance. So invariance means that basically it doesn't matter in which order you do. You have a function, you shift it, and then you measure the Radon transform, or you measure the Radon transform, and then you shift the measurements, right? So some notations, the 2 stands for the dimension. So A is the shift, so you're making, this is a vector, right, in R2. And then the 1 stands for the 1 dimension, and you're making a 1-dimensional shift with S. So this is a shift in the Radon transform, where you're shifting the distance of the line from the origin, and this is where you're shifting the whole function in the plane. And again, it's a very simple algebra. You just write down the definition of the Radon transform, do a simple change of variable, call this by y. Clearly, the shift doesn't change your measure, and you do this, you'll see that it really doesn't matter if you first shift the function and then measure Radon transform, or whether you do the Radon transform and then you do the shift of the Radon, the 1-dimensional shift of the Radon transform. And why is this important? So mathematically, there is some. I'll try to make it in a hand-waving way, but there is this idea that if you have shift invariance, then doing Fourier transform would help you. And let me give you a hand-waving argument why it is true. So let's say I'll be very often doing some parallels with linear algebra. Okay, let's say I have a matrix and I'm trying to invert the matrix. If you would have the choice to invert the matrix, which matrix would you invert? Don't tell me identity. I mean, that one is okay. That's the first choice. If it's not an identity matrix, what kind of matrix would you like to invert? Diagonal. Diagonal is easy. Why? Because you invert element by element. So now if I'm trying to invert my Radon transform, if my Radon transform was diagonal in some sense, that would be really nice, because then I would do it component-wise, right? And diagonal is basically what that means is that in expansion in a certain basis, you only have you can diagonalize the matrix if you change the basis, right? And then in that basis, you have only one component range. So here's the thing, that if you think of now in infinite dimensional spaces and so on, think of exponentials. Exponentials are eigenfunctions of shift operator. I didn't say, right? E to the I, e to the lambda x. You make a shift, you'll see that it's an eigenfunction of the shift operator. You can also, with the little work, show that it's an eigenfunction of any operator that commutes with shifts. If you have an operator that commutes with shifts, it's shift invariant, then exponentials are eigenfunctions. Moreover, the exponentials in some sense are orthonormal. You can make rigorous meaning out of it. Now again, going back to linear algebra, guys, remember if you have an orthonormal basis of eigenvectors, then your matrix in the orthonormal basis of eigenvectors diagonalizes. That's exactly how you diagonalize things. So if you have an operator that is commuting with shifts, if it's shift invariant, then passing in some hand-waving sense to a basis of exponentials is very useful. Then you can, in some quote-unquote sense, diagonalize your operator, and then things become nicer. So I have 2 types of shift invariance here. One is this, and the conclusion here is that doing Fourier transform may be helpful, and I'll be doing a lot of Fourier transform today. There's another type of shift invariance, which is shifting the angular component. So that's rotation invariance. So if you think of shift but in theta, I have rotation invariance, and that's, again, algebraically, it's very easy to compute. So if A is a 2x2 rotation matrix, then this MAF is you basically rotate the plane and then you take the function. And then let's see what happens if you measure the Radon transform. If you measure the Radon transform of the rotating thing, well, this is the definition. Then you do the change of variable. Clearly the measure doesn't change, right? You don't stretch anything. And then I can rewrite this like this. Why is that, guys? Why is a minus 1 y dot omega goes there? I have to put it's an orthogonal matrix, so the inverse is the same thing as the transpose, so you should throw it there. Okay, very nice. And then you immediately get this. So you see, it doesn't matter if you first rotate the plane and then do the Radon transform, or whether you take the Radon transform and then you rotate. And by rotate, I mean do a shift in the angular variable of your lines. Right, so that's your rotation invariance, and the rotation invariance tells you, again, in the sense that I was describing a minute ago, that if you go to Fourier series, then things would be nice. In fact, today I'll show you one of the inversion formulas is the Cormack inversion formula, which is based on the Fourier series, and he diagonalizes the Radon transform in the basis of exponentials, and then he inverts coefficient-wise. Just like in matrix, you invert every element on the diagonal, you can do the same thing with the Radon transform when you go to the Fourier series, and then the other one would the previous one would show up in the Fourier slice theorem. Okay, and there is one more invariance. That's the dilation invariance, and again, you can do it algebraically. The definition of the dilation is you multiply the variable by a, and again, if you do the algebra, you do your change of variable, you will see that it's almost invariant. You have to have a coefficient in front. But basically, if you do the dilation to the function, it's the same thing as if you do the dilation to the Radon transform with some coefficient in front. And with some, again, hand-waving logic, the dilation tells you that the Snelling transform may be helpful when you try to invert the Radon transform, and there are some formulas involving Snelling transform as well. Okay. So this is what I was planning to say yesterday, so this is the end of the yesterday's talk. I'll switch to the other slide, but before I go there, I wanted to give some references, especially for those of you guys who haven't seen this field before, you've seen a little bit of it. This is written in alphabetical order, so it's not in the order of importance. This is a very recent book written for anybody who has an undergraduate background in mathematics. A very nice introductory textbook. If you are just starting this field, I think this is an excellent place to see the basics. Written again, if you have had calculus 1, 2, 3, linear algebra, differential equations, and some analysis, you can understand and read everything here. This is the easiest one. The last two books by Frank Natter, they have had several editions of this book, are so important in this field that they have nicknames. For everybody who deals with tomography, they know that the nicknames of these two books are the Old Testament and the New Testament of tomography. So this is basically the Bible of tomography, the two volumes. Very nice. Of course, this requires a little bit more than an undergraduate background in mathematics, but he has nice appendices where he discusses things and so on. Helgeson's book is a comprehensive book on Radon transform, very nicely written, a little bit harder to read, in my opinion, than the Natter books. Gelfand Dicky Drive is a very nice book on integral geometry. This is in general, integral geometry, by the way, is a term that has two different meanings somehow, and this is in terms, not surprisingly, this is the Gelfand sense of integral geometry, which is the part of inverse problems that deals with recovering functions from their integrals along curves, surfaces, hypersurfaces, submanifolds, and so on. Nice book, but this is kind of, a lot of things here are state-of-the-art, very, this doesn't involve, this is not an introductory text. If you are more advanced and you want to see some more interesting developments, this is the book to look. The upper two are more tilted towards applications. So there's a lot of discussion about numerical approaches, inverting things, and a lot of discussion about the applications and so on. Okay. How do I go again? Alt F. Alt F, that's what I'm trying, and it's not working. expressions. Okay, so now I want to go to the uniqueness, injectivity issues, and inversions for the regular Radon transform. Again, most of what, almost everything about the regular Radon transform is known for a long, long time, but a lot of the things that we do here would give us ideas how to treat the new types of Radon transforms, although of course not everything works, but some of this is going to give us ideas. Plus, I think many of you have not seen it, so I would prefer to stop on this a little bit. So I'm going to use a little bit of abuse of notation. Omega is of course a vector, but RF omega d is the same thing as RF theta d with the omega d in one-to-one correspondence with theta. So the first inversion formula is going to be related to Fourier transform, so I wanted to make sure that we're on the same page with the notations. The tilde stands for two-dimensional Fourier transform. The hat stands for one-dimensional Fourier transform. And then I'll be doing a one-dimensional Fourier transform on on the function that's defined on the lines. And I want to emphasize the fact that I treat omega as a parameter, so everything would be done to the distance variable. Okay, so if you see g hat, that's a one-dimensional Fourier transform with respect to this variable. And everything else is the standard notation. So tilde is two-dimensional, hat is one-dimensional. Okay, so here is the first inversion formula that was known to Radon himself at the beginning of the 20th century. It's an exact closed form inversion. And here's what it says. If you have the Radon transform of a certain function, do a one-dimensional Fourier transform to it, and with some coefficient in front, you exactly have the two-dimensional Fourier transform of the function. So if you want to recover the function, do a two-dimensional inverse Fourier, then you'll have your function back. And somebody yesterday was asking me about the connection between Fourier transform and Radon transform. This is probably the most classical connection. So the proof is two lines. We just rewrite the definition. We'll rewrite the transform. This is the definition. Now let me make sure that everybody can see what we're doing. So if this is the Radon transform along the line at distance d, so if this, t, if this distance is t, and this is the unit vector omega, then when you do omega t, you end up right here, and then omega per is the vector in this direction, and then s is measured basically along the line that you integrate. So what I'm saying is, well, go from the origin, jump on the line, and then do the integration along that line. Clearly, s will be then the output. So this is another way of writing the same thing. Okay, so now if you do a Fourier transform, again, we're doing Fourier transform with respect to t, one-dimensional Fourier transform. This is the definition. Haven't done anything, just wrote down the definition. And then if you look at this, guys, then basically you have now integration with respect to s, and you have integration with respect to t. So t is in this direction, s is in this direction. They are perpendicular, so you have dt, ds. So you're basically integrating along the whole plane, orthogonal axis. And you can do a change of there, basically a rotation. You'll see that you will have an integral of f. If you call this by x, then some simple algebra will give you exactly that. And you will see that here you have a two-dimensional Fourier transform, but you need to add another copy of 1 over square root of 2 pi to have exactly the two-dimensional Fourier transform. That's why you'll have to add that on this side. That will be your proof. But if you put 1 over square root of 2 pi, then you would have 1 over 2 pi, which would be exactly the two-dimensional Fourier transform. Okay, so this is the connection, and it's very, very geometric. You see that you're not doing anything other than saying that, okay, if you're integrating along lines, if you integrate in the perpendicular direction, then you're integrating along the whole plane, which would give you two-dimensional Fourier. This was known to Radon, but for some reasons, numerically, the implementation of this formula was not very stable. I guess FFT was not known at the time, and there were some other issues. So people have been trying to come up with other types of inversion for the Radon transform, not only for numerical implementation, but for several other reasons. And I'll talk about the necessity of other types of inverses as well. So let's go and see if we can find some other types of before I go to another type of inverse. Of course, this also gives us a uniqueness result. So in particular, if f is an L2 function, and you know that its Radon transform is 0, then you basically know that the two-dimensional Fourier of your function is 0. That means that your function is 0 almost everywhere, so that's a uniqueness result. In particular, in tomography, we're dealing with compactly supported functions, so you know that the full Radon data is enough to recover your function uniquely. Okay, and this is the inversion strategy. So if you want your function that you have the Radon, do a one-dimensional Fourier, then a two-dimensional inverse, and you have your function back. Okay. So now, back projection is the dual operator of the Radon transform. So dual in the L2 sense. So if you take an L2 product of your Radon transform with some other function defined on S1 cross R, and then you're looking for an operator on G such that this inner product is equal to F R sharp G. And it turns out that that operator has a nice geometric meaning, and the result is stated here as a theorem. I don't have the proof. It's a nice simple exercise with change of variable and interchange of the order of integration. I would rather stop on the geometric meaning of this operator. So I want to discuss what the back projection does. So we're trying, so the back projection operator is an operator that takes us from the world of lines to the world of x and y. So let's say I'm trying to back project in this point x1, x2. x1, x2. So I want to see what this thing is. So I'm averaging the function g, and that function g is defined on lines. G lives on the space of lines. So I'm averaging the value of g on some lines, and what I want to discuss geometrically is what are those lines at which I'm averaging the values of g, right? So let's look at this. Omega goes all along the unit circle, so my lines should rotate. I would have to have the lines at all different angles. And simultaneously, the distance changes. For every choice of the angle, I have a very specific distance. And if you look, it's very nicely chosen so that for a given, so let's say I choose omega like this. Let's say I choose omega like this. If this is my omega, there are so many lines with that omega. How far should I go? The line at what distance should I choose? The distance is x times omega, and x times, if this is the vector x, and x times omega is exactly enough distance so that the line with that angle passes through that point x. Now, if I change omega and rotate it, again, there are plenty of lines to choose. Which one do I choose? Well, the one exactly that passes through this point. And so basically, the back projection operator says if you have a function defined on lines, average the values of your function for all lines that pass through that point. Okay, so for this line, you have a value of the integral of your function f. For this line, you have the value of the integral along that line of function, and so on. You average all over those values, and you assign that number to that point. That's what the back projection operator is. So this is the world of x and y, and if this was the world of, say, minus pi, 0, 1, this was the world of sinographs, then I'm integrating the function g defined here, I'm integrating along a certain curve, and every point of that curve corresponds to a line, and the set of those points correspond to all the lines that pass through this point. So RF takes you from here to here, F was defined here, RF takes you here, R sharp takes you from the world of lines to the world of the x and y. Okay, so we want to see what happens if we apply R sharp to R. So this takes me from this world to this world, this takes me from this world to this world. If I apply them successively, would I get my function back? That would be very nice, but it's kind of too good to be true. So if this back projection operator would be the inversion, that would be the best. Unfortunately, it's not quite that, but it's not that. It's close to that. So there is a name for that. It's called the normal operator. If you take your operator, apply to that the dual, you have this normal operator, and let's write down the definition and see what the normal operator does. So, okay, well, we write down exactly the backprojection applied to the Radon transform. You do the, let's see, so, yeah, then we rewrite the Radon transform. So right now inside I have simply written the definition of the Radon transform. And now what you guys have is, this is basically double of the integration in the plane if you think of polar coordinates. So if you substitute it, instead of integral from minus infinity to infinity, you have the integral from 0 to infinity, you actually have exactly integration in polar coordinates along the whole plane, but you will have to take care of the Jacobians. You will have to multiply by the distance and divide by the distance. So you will have two copies of integration along the whole plane in polar coordinates. So that's where the two come from. This is the we compensate for the lack of the Jacobian there. So this is what we have. And if you look carefully, this is simply the convolution of my original function with this 2 over the absolute value of x. So again, you see, I started with f, then I did Radon transform to it, and then I did the dual to it. And it turns out that the action of these two together is simply a convolution operator of my original function with this guy. Now, what does convolution usually do, guys, to the functions? It smoothens, or in terms of images, it blurs, right? If you would have the choice, again, if you have the choice of choosing something to convolve with, what would you convolve with if your goal is to recover f? Delta function. If you convolve it with delta function, then you get your function back. That's the unit in convolution sense, right? Well, I don't quite have delta function, but it's kind of like delta function, right? I mean, if you think about it, this thing blows up to infinity at the origin, and it decays like a hyperbola, but okay, it's not quite delta, but it's almost like delta. So what happens is, if you have a function, and then you have this Radon and you apply the dual to it, you don't get your function back, but you get a blurry version of it. So the next task would be somehow to deblur it, somehow to sharpen it. And in imaging, there is people call it filtering. So you would like to filter it to get rid of the blur, to make things a little bit sharper. And the next thing is, what would be this filtering, and how would I impose this filter so that instead of the blurry version, I get some sharp version or the exact version of my function. Okay, so we want to deblur, and for the deblurring, I'll go to the central slice theorem. By the way, I forgot to say that thing has a gazillion of names. So this theorem, some people call it Fourier slice, some people call projection slice, some people call central slice, but some sort of slice. And again, slice because you saw how we got that, right? We had slices and then we integrated across. So we got the integration along the whole plane. Okay. So again, what we're going to do is we're going to do some algebraic manipulations that would lead us to something that is going to give us a nice inversion formula. So I start with my function, and this is the inversion for this two-dimensional Fourier inverse Fourier transform, two-dimensional case. Then I go from the Cartesian coordinates to the polar coordinates. Okay, and then I just like a second ago, we went from minus infinity to infinity to double from 0 to infinity. Now we're doing the opposite process. That's why the compensation I have, instead of 1 over 2 pi, I have 1 over 4 pi. And so then you will immediately see that if we apply this thing to the, let's see, right, so, yeah, so the interior part, if you change the order of integration, if you change the order of omega and sigma, this guy goes out, then inside you would have the Radon transform, right? So let's see. We have this 1 over 4 pi s1. No, I didn't change the order of integration. What am I doing here? No, sorry. I'm applying, of course, I'm applying the central slice theorem. Of course, I'm applying the central slice theorem. So by the central slice theorem, remember the two-dimensional Fourier transform of f is one-dimensional Fourier transform of the Radon transform. So I'm not changing the order of integration. I'm just substituting the two-dimensional Fourier of f by one-dimensional Fourier of the Radon transform. And this is going to give us the exact inversion formula, and this is what we will call the filter back projection formula. So the filter is kind of hidden here. It will be more clear in a second, but look, I am recovering the function from the Radon transform. So G is the Radon transform of my function. So this is a Radon transform. I do one-dimensional Fourier to it. Then I'm multiplying by the absolute value of the frequency variable. After the Fourier sigma is my frequency variable. Then I'm going to do an inverse Fourier to it, and then back projection. The exterior integral is back projection. So what this filtering is you take the for your Radon, you go to the Fourier domain, multiply by the absolute value of the frequency variable, do an inverse Fourier, and then back projection. And it turns out that this intermediate step is your filter. The intermediate step guarantees that you recover not some sort of fishy, blurry version of your function, but you recover exactly your function. So let's introduce some notations. The absolute value of the frequency variable can be written in this form. I separate the sign, and I squared cosine minus 1. The reason we're doing it is because that will give us exactly one of the definitions of the Hilbert transform. So if you have a function, you take its Fourier, multiply by the sign of the frequency variable, and then do the inverse Fourier with some constant in front, then that's called a Hilbert transform. So the previous formula simply says that this integral can be written as derivative with the Hilbert. The derivative is because, remember that the derivative and the Fourier transform are related by this multiplication by the frequency variable. So your function is recovered in the following way. You have the Radon transform, you differentiate it in that second variable, then you do a Hilbert transform to it, and then back projection. With some constant, you recover your function. So the filtering part, remember before, I didn't have this HDDT. I had RF and R sharp, and I was recovering the blurry version. It turns out that this HDDT is my filter. So if before doing the back projection, you do this operation, that's your filter. That's what helps you to sharpen the image. Okay? So the filter that we were looking for, one of the versions, would be this thing. Now, the Hilbert transform has another form, another definition. It will be, of course, a theorem to show that the two are equivalent. And this is the other way. You don't need to do any sort of Fourier transform or deal with any complex numbers. You will have to do, as opposed to Professor Bowman, I'm writing principal value as PV. So the Hilbert transform will be defined as the principal value of this integral. So the filtration is this, and you can do the filtration just with real variables without any Fourier stuff. There are a couple of other ways of filtration. One way of filtration would be to do it afterwards. Remember, the previous one was in the middle, between the Radon and the back projection. We had this Hilbert as a derivative. That was my filtration. You can do filtration afterwards. So when you generate the blurry image, you do something, and that recovers your function, and that something is the so-called Calderon operator, which is the square root of minus Laplacian. What would be like a half degree of Laplacian? How would you guys think of a half order of derivative or 3/4 of the derivative and things like this? How do we define it?
Eigenvalue of minus Laplacian. Self-adjoint operators.
Yeah, but you can do it in the Fourier space, right? You can go in the Fourier space, you multiply by IXC to a certain degree, and that gives you the degree of your differentiation. If you make it a fractional, then you can define your fractional derivative like this. And in fact, we can have some. There is a whole family of filtering, and that family of filtering is done through this so-called Riesz Potential operator, and this is exactly what we were just discussing. So you do the Fourier transform in the Fourier domain, you multiply by a certain degree of your frequency variable, and then you would have to do the inverse Fourier, and this theorem gives a whole family of inversion formulas where the filtration can be done either before or after, or part of it before and part of it after. Depending on what value of alpha you choose, you can get a whole lot of different families of inversion for the Radon transform. I don't want to spend time on proving this, but this is very well written. For example, in Natterer's book, if anybody is interested, you can look at the Natterer's book for the family of inversions of the Radon transform with Riesz potential operators. Okay. need so many inversion formulas, guys. As I said already, that sometimes it may be about numerical implementation, but there is something more to it, and that something is related to the range. We talked about it already. Professor Riesz talked about it, and I mentioned it yesterday during my lecture. So again, I want to go back to something simpler, to linear algebra, show some examples, and then make some more general conclusions for the necessity of different inversion formulas. So let's say I have these matrices A, B1, and B2. A has a trivial kernel. That's going to be important in a minute. So in other words, if AX is equal to 0, and then X has to be equal to 0. And then B1 and B2 are left inverses, right? Left inverses means that if you multiply from the left, you get an identity. That's very easy. You can check that. And none of them is a right inverse. So if you multiply them from the right, dimensions are okay. You can multiply them. But if you do that, we'll see that you don't get an identity matrix. And the problem with that is that then, you see, if you take this y is equal to ax, then if you multiply from the left, b1y and b1y and b2y are the same thing. However, if b1z is not equal to b2z, if z is not in the range. So if you're trying to do the inversion for something that is not in the range, you're in trouble, right? And why is this important for the Radon transform? It is important for the Radon transform because all the inverses that we have generated so far are left inverses. They're left inverses, and that means that if you are trying to apply those procedures, formulas, algorithms to something that lives in the space of the correct variables, say S1 cross R, but they are not in the range, then each one of these inverses may produce something different. So I will show you a couple of other inversion processes. So let's say I take a random, let's say I take a function g of theta d, where theta lives in a minus pi pi, and d lives in R. If I somehow out of the blue come up with a function like this, and I try to apply inversion processes to this thing, trying to recover f, if this is not in the range of the Radon, if there is no f for which Rf is equal to g, then those processes, inversion processes, will produce something, but that something would be different, may be different for different inverses.
This is relevant when you make errors.
Exactly. Why is this relevant? Because every time you make measurements, you cannot expect that your measurements are going to be in the range. And so when you're applying your inversion process, you're applying to raw data, it's most probably out of the range, so some of them may be good closer to the reality, some of them may be farther from the reality, some of them may be stable, some of them may not, some of them may be numerically easier to implement, some of them may not. So that's the reason why we need more and more, it's not that it's an ever-going process, but it's not useless when people generate new formulas. And the next thing that so this is about the errors, why the range description is important, and this is exactly what I said. So the next thing that I want to talk about is another way to invert the Radon transform, and this is related to the rotation invariance and the use of Fourier series. So here's what I'm going to do. Again, I'll assume that my function f is supported in the unit disk. But instead of using Cartesian coordinates, I'm going to use a polar coordinate. So f is going to be a function of r phi with the obvious wrong parameterization. And then I'm going to expand my function into a Fourier series where the coefficients are going to be functions of r, but because it's periodic and phi, everything is nice, so I can expand it into Fourier series. I'm going to expand into Fourier series my data. Again, I'm going to expand into Fourier series with respect to the angular variable. S is going to be a parameter in the coefficients. And as we discussed before, the hope is that the Radon transform will diagonalize when you pass to the basis of exponentials. So this is the basis of exponentials in both cases. And this is, of course, the definition of the Fourier coefficients. And here is a theorem due to Cormack. which he got a Nobel Prize in medicine. The work was done in 1963, the prize came in 1979. Because this work allowed to create the CT, the computer-assisted tomography, and it was really a revolution in medicine, and it was a well-deserved prize. Although, as I said, for example, the Radon inversion, the analytic inversion was known long before, and even the Fourier series inversion has been known. This inversion has been known to people in astrophysics for 20, 30 years before it. But as usual at the time, a lot of people in different fields operate independently, so one doesn't know what the other is doing. And this thing came out at the right time for the right problem, and it worked. So here's what it says. It says that if you write the Fourier coefficients, and you write the definition of the Fourier transform, you will see that the operator diagonalizes in what sense? You see, there is f, and then there is rf, which is g. So if you represent this f through its Fourier coefficients, infinitely many of them, and you represent this g through its Fourier coefficients, infinitely many of them, this relation tells you that these coefficients are related. But in general, F32 may depend on all infinitely many of G's, or F55 may depend on all of them. There is no reason why F32 should depend only on G32. And that's, in fact, that happens, and that's the diagonalization. And the reason that happens is because of the rotation invariance and so on. So when I say that the Radon transform is diagonalized, but by that I mean that the nth Fourier coefficient of the function depends only on the nth Fourier coefficient of the data and vice versa. So when you write down this relation, you'll see that the relation is like this. This is the nth Fourier coefficient of the function. This is the nth Fourier coefficient of the data. These are the standard Chebyshev polynomials, and you have this kind of integral equation. So the goal, again, is to recover f from g. So you want to solve for this unknown function from this integral equation, which is a standard Abel-type integral equation. There is a standard way of approaching this type of problems. And in fact, in this case, one can explicitly find the solution. And it turns out that if you solve this, the nth Fourier coefficient of your function can be recovered by taking the derivative and doing some integration, you resolve the kernel and whatnot. So this is the final formula. So having your Radon transform, you find its Fourier coefficients, then you differentiate them, then you plug them in here, and then you recover your Fourier coefficients of your function. And okay, depending on what accuracy you want, the numerics of this becomes a different story. How many do you keep, how many do you cut, and so on. But this was used in the first tomographic machines. This is how they were recovered. Sorry, I didn't hear it. This one is derivative with respect to s. Yes, it's first derivative with respect to s. Okay, so typically, I want to say that typically the backprojection type formulas, filtered backprojection type formulas, are much nicer for the numerical implementation, and they are considered kind of a golden standard. These type of formulas are in ASCII usually because you have to really struggle of how many coefficients to keep, and very often in other generalized radon transforms you will see that the resolvent kernel is not so nice, and things can be complicated. But you have already seen basically three types of formulas. The filtered backprojection type formulas, where basically we had a whole family of those, and then the Cormack type inversion formula. So later in my lectures you will hear often I will say Cormack type. That means that instead of recovering the function, one tries to recover the Fourier coefficients of that function. And the third one was the Fourier slice theorem, which was done by Radon himself. Those are nice and closed form, but very hard to deal with numerically. Okay, so some additional remarks. This is something that I said yesterday, that in Rn, Radon transform is integrating along hyperplanes. If you want along lines, it's X-ray transform. And for Radon transform in higher dimensions, there are inversion formulas similar to the Riesz potential type formulas that we discussed. There are Cormack type formulas in higher dimensions. Instead of, for example, in 3D, instead of using Fourier series, you would have to use expansion into spherical harmonics and things like this. but there are similar formulas in higher dimensions. And there is a whole set of problems that I didn't touch, and if I have time, I may come back to this in lecture 4, but yesterday we had a small discussion with somebody in the audience, the so-called incomplete data problems. So far, everything that you saw was done under the assumption that I have my radon data for all their values of the angle theta and for all the values of distance d, all the relevant ones, because after a while, if it's a compactly supported function, you don't touch anything. But there are a lot of incomplete data problems where, let's say, you don't have certain angles. Let's say you can only go with angles between 0 and pi over 2. Or that means that you have like lines like this up to lines like this, right? You rotate only, you only have half of the data angularly. Or let's say there are situations when you don't have lines passing through a certain region. They are all coming, well, most of them are coming from applications. If you're trying to find an image of a patient, it's very bad if you send X-rays to the spine cord, especially if it's a patient that is going through some sort of treatment and you need to monitor that patient regularly. You're putting that patient into the CAT scan regularly. If you send this radiation through the spine cord often, then you're ruining the patient's health. So there is this so-called exterior problem where your function is supported, let's say, in the whole disc, but this is some sensitive area, and you have all the lines except the lines that go through here. So this line is not available, this line is not available, and so on. Can you recover still the function? Even if you want the function just in the angles, can you do that? There is the so-called interior problem where it's the opposite. Let's say your function is supported in the larger disk, but for whatever reason, you have only lines passing through a small subdisk. Can you recover the function uniquely or not? There is another set of problems with incomplete data, which is very realistic. Every time you do measurement, you don't have full data. You have to discretize. Instead of a continuum of angles, you have, I don't know, 128 angles. Instead of continuum of distances, you have 128 distances or something like this. How does this affect your inversion? All of the theorems that people prove are done under the assumption that you have full data. Moreover, most of the time, as far as functional spaces go, if you, for example, look at the book of Matterer, every theorem is proved for functions in the Schwarz space. And it's a natural question, where are you going to get a patient with a C infinity interior, right? So it's a completely different topic of finding out what happens if you give up those conditions. There's a lot of research done and being done for different modalities, different types of radon transforms. It's all interesting, but I don't think I will have time to get to that. Okay, so let me talk a little bit about the circular radon transform, and then we'll see how I think I have about 6 minutes or so. So this is, now I'm going to the circular radon transform, and that's the thing that came up in the ultrasound reflection tomography, thermoacoustic, and photoacoustic tomography. And if for the case of the regular radon transform, in 1960s and 70s, most of the important things were done already. This stuff was developing in the last decade. I think most of the important things in this one is also almost done, but this is very, very recent, like a decade or so. Some work has been done actually 20 years ago, like Agronovsky and Quintos' result is from the 90s, but a lot of work was done in the last 10 years. So I'm going to talk about the uniqueness, injectivity, and some inversion formulas, and see how far we can go. So we talked about this already. The count of dimensions tells us that we cannot, and the applications tell us we cannot have all the centers, right? We cannot put the microphone inside the patient's body. I want to remind you, we're trying to recover a function, let's say, supported in a disk from measurements from integrals along circles. Now you can take the integrals along circles with centers along the curve. One choice would be to put those centers on the edge of the object. If your object is perfectly circular, then that would be the nicest case. Sometimes you can try to put your detectors along the line. By the way, we did say that the line is bad, but I forgot to mention one thing. That remember we said that the kernel of the transform like this is non-trivial, and we said at least every odd function is there. Right? Every function that is odd with respect to this line gives you 0. What I didn't say is that is it. In other words, if your function is even with respect to the line, then there are unique reconstruction formulas. And because you can write any function as a sum of even and odd, you can claim that the even part you can always recover. Or think about it like this: if your function is supported only on one side of the line, you can recover that function. So the linear detectors are not bad if you know what you're doing. And of course, there are many other ways to match the dimensions. If you don't think of the applications, in fact, there are many interesting results about inverting the Radon transform from two-dimensional data with different types of two-dimensional data. For example, you can take all the circles that pass through the origin, or all the circles that pass through one point. If you consider the family of circles passing through the origin, that's two-dimensional family, because all you need to do is define the location of the center. The radius is defined immediately because that's the distance to the origin. Or you can take all the circles that touch a certain line. That's a two-dimensional family, and you can, it's a very nice mathematical problem. Try to come up with inversion, or is it injective or not, and so on. There are many, many different ways. The reason that I'll be talking about the ones that I'll be talking is motivated by the applications. But if you're interested in pure math, you can come up with all kind of nice setups. And there are plenty of unsolved problems in that sense. Okay, so for which values of the centers and radii does the knowledge of the Radon transform allow the recovery of F? And simultaneously, I will be talking also about the elliptic transform, for which values of the locations of the foci, E stands for the emitter, R stands for the receiver, for which values of the locations of the foci does the knowledge of the elliptic Radon transform allow unique reconstruction of F. And this is the example that we talked about, that the line is not good, and the kernel consists of only odd functions. In fact, that result is in the classical math physics book of Courant and Hilbert. It has been known for a long time. And that brings us to the definition of the injectivity sets. The Radon transform is called injective or a certain set. And this set, this is the locations of the center. This is the radii, because there is another. So far, we're assuming that you have all the radii. But remember, the radii correspond to the time. You're saying, well, if I sit there and measure forever, then I can do something. You're not going to measure forever. Or that radii also correspond to the depth of penetration of your signal. If you have a bone and you have an acoustic signal, you're not going to go behind that. Or if the patient has a metallic implant, you're not going to go beyond that. So the data may not be also complete in the radius. So the set of injectivity is a subset of the location of the centers and the available radii. So the set is called injective on a set S cross T for a certain class of functions F if the fact that the Radon transform is equal to 0 implies that the function is identically 0. So if you're sitting there and you don't hear anything coming out, does that mean there was nothing to start with? Or is it that your set is not injective? And by set, now again, I mean not just the location, but also the time. And you can ask the same question in case of the elliptical transform. What location of the foci and the time you need to be able to recover the function uniquely. There are some really nice results about this for circles, very little is known for ellipses, and some big open problems even for circles for higher dimensions and for classes of functions that are different from compactly supported continuous functions. So I'll stop here and I'll continue from here tomorrow.